specified position of this steel by as much as half an inch in a 6-inch slab, it weakens the slab capacity by 20%. Furthermore, on the bottom of the next page, it's indicated that there must be adequate spacing between the bars and whatever the slab would be, and the minimum must be 3 times the thickness of the slab. You don't want a space greater than 3 times the thickness of the slab. Furthermore, as indicated here, as long as the number of bars is maintained, a reasonable tolerance of spacing of bars is allowed, and that can be plus or minus 2 inches. On page 10-9, it's indicated that stirrups, which are an additional component that wrap around the bars to keep them stable, they also have a tolerance limit of plus or minus of 1 inch. On page 10-10 in my edition, some other information. Bars stopped in 60-foot lengths, and you can get larger bars. And this chapter generally is going to now talk about splicing, and there are various types of splicing it will refer to. For example, lap splices, just lapping one piece against another, and they're more economical than other types. There are limitations, however. Lap splicing of number 14 and 18 bars is not permitted. A mechanical fastening device known as a lap splice connector is shown here. Another item pointed out here is that the code only permits field bending of partially embedded rebars, assuming that it's approved by the engineer. And now the book is going to show a variety of mechanical connectors and their names. On page 1025 of my edition, we see some examples of welded splices, and they indicate they're lap splices and butt splices. The next page indicates that tack welding is not permitted. On 1027 of my edition, we see a picture and then a discussion of the size of the tie wire and number 16.5 or number 16 black soft annealed wire. On page 1028, we have an example of a snap or single tie. On page 10-30, we have a list of tools that are used. At the bottom of the page begins a discussion of general principles of tying bars, and notice that it's not necessary to tie bars at every intersection. Chapter 11 deals with placing bars in footings, walls, and columns. On page 11-3, we see an example of a continuous wall footing, another configuration. So here we would see the type of use of steel in a concrete footing around a rectangular house, for example. After discussing the placement of dowels on page 11-8, there's a discussion about the bending and rebending of bar. Notice there's a limitation of about 20 degrees or 3 inches per foot, with the vertical is the maximum acceptable. On page 1120, we see a table that indicates what's called the universal standard, and this is a placement of steel in columns. Another method of placing the bars is the ACI standard, shown on the next page. Chapter 12 deals with placing bars in floors and roofs. And on 12-2, they take you through the steps of placement, starting with beam bolsters. In addition to normal bar placement, on page 12-4, they indicate that there is occasionally a need for a smaller bar simply to hold up the stirrups and ties, and they call for the use of a number 4 bar, and these are called stirrup support bars. Another use of bars is for what is called temperature reinforcement. This can be done with bars or with welded wire fabric. On page 12-12, we see the proper placement of bars in stairs. Chapter 13 deals with placing bars in post-tension floor systems. There has been some focus on post-tension systems recently, so looking this couple of pages over wouldn't be a bad idea. You also have discussion of post-tension systems in walkers. Chapter 14 and 15 are dealing with subjects that are not usually tested on. Chapter 16 deals with the inspection of reinforcing steel, so this is where you'd want to pick up and mark in your book. Chapter 17 deals with safety precautions. Chapter 18 deals with corrosion protection systems. And notice that this chapter indicates that zinc is a coating that is often used, as well as the use of epoxy-coated rebar. A special note about epoxy-coated bars on 18.2 is that the coating must stay consistent, so we have to avoid scratching or otherwise damaging it. Also, on page 18.4, tension lap splices of epoxy-coated bars are usually longer than those required for uncoated bars. On the next page, there's a final discussion on zinc-coated rebar and epoxy-coated welded wire fabric. And finally, there's a pretty good glossary at the back of this book, which you should know exists, but may be necessary to refer to it during the exam. And that concludes our review of placing reinforcing bars. If you look at item C on your outline, it talks some more about math calculations. Now, we've already discussed a number of calculations that you'll need to be able to make for this topic. Here we're also indicating that estimating rebar is something you'll have to do, the length of the rebars, estimating concrete. And one of the skills you'll want to develop for these two estimating problems is you're going to want to be able to understand how to come up with a centerline perimeter. We talk about that in the CRAM workbook. We talked about that in the first module. Because if you're estimating rebar, for example, there's two ways you can place rebar in a footing. The first way you can place it in a footing would be as if you were building a rectangular house, and you have a footing, and this rebar is being placed in the footing continuously all around the rectangle. So, for example, you might have such a footing, and you might be instructed to place 3 number 5 bars in this footing. And you might need to find out the total length of these bars. The easiest way to do a calculation like that is to find the centerline perimeter around that footing and then multiply it by the number of bars that are involved. So the centerline perimeter times 3 would give you the number of lineal feet of bars. And usually with rebar questions, you eventually translate that into weight. So you would look at the table showing you the weight for a given type of bar, and you would do the appropriate multiplication and come up with the weight for all the rebars. Another way, however, to estimate rebar has to do with layering the rebar like a tic-tac-toe pattern, for example, in a small rectangular footing. Both of these methods are described in the CRAM book, and you're going to want to feel comfortable that you can do these kinds of calculations. You already know by now that you're going to have to do basic conversions, and the CRAM book lists many of those conversions. In the 10th module, we will focus more on reading plans, another skill to be developed. We've already introduced you to the notion of reading tables, and you want to get practiced at this skill. And then you have some specialty types of problems, such as a weight on a choker, the weight of 1 cubic foot of steel, or the weight of a given amount of steel, and some other types of rebar calculations, all of which are indexed in your CRAM reference books, and you're going to want to get familiar with these. Roman numeral 5 in your outline deals with formwork. We're going to be taking a look through M.K. Hurd's Formwork for Concrete. Now, this book is a copyrighted book. This informational showing is for reference and instructional use only. It is necessary for you to obtain this book as a part of your state recommended reference books for the exam. We can begin our conversation by one of the most important features of this book, which is really the prevention of failures. These circumstances are highly dangerous and often involve the loss of life. And so in dealing with formwork design, of which the contractor is responsible, it is necessary to consider why concrete forms fail. The most important or first primary reason of failure is improper stripping and shore removal. It's vital that you obtain the required tests at the required times and not try to remove forms until the concrete has reached its proper designated strength. Another cause for failure is inadequate bracing. Excessive vibration is also a major reason for formwork collapse. And unsuitable soil is also another reason. Inadequate control of concrete placement and lack of attention to formwork details are two other major reasons why formwork fails. And the point of this conversation, both for the exam and also for real life, is that in dealing with formwork, you have to consider the aspect of safety. The actual rules for formwork placement are incorporated into the building codes, and you will see various designations such as ACI 318 and other ACI references. You will also see ANSI. These designations are of organizations, and they provide information, research, and testing that then sets standards for applications. The ACI, the American Concrete Institute 318, is often adopted into building codes and does explain the rules and regulations for developing formwork. On page 211 of my edition, and a similar page if you have a different edition for you, one of the issues involved in formwork has to do with the subject of contact surface area. In other words, if I'm going to pour this wall of solid concrete, I'm going to want to put formwork up, but do I want to cut out for this little window? What is the rule of thumb here? And the rule of thumb is that if we have an opening that's larger than 30 square feet, we're going to go ahead and cut open the form for that. But if we've got something smaller than that, we're going to provide for it so we don't cover the window and pour over the window, but we're not going to necessarily have to cut the form out. Now, as a math problem, contact surface area has been asked on this exam, and it very much parallels the elevator pit problem. If you can remember, the elevator pit problem is a rectangular pit that has thickened walls. And the shaft of the elevator attaches to these walls and goes up through the building. And the bottom line is, if I had to figure out the contact surface area for the shaft of an elevator pit, what I'd essentially do would be to get the centerline perimeter around the pit, multiply it by the height of the shaft, and then multiply it by 2. And that would give me the contact surface area for both the inside and the outside of the shaft. Then I would have to consider the openings I would need to make for every elevator door. So each floor and each elevator I'd have to open up for the door. And then I'd have to add back in these little pieces that would go back in to make sure the concrete didn't pour through the door opening. So contact surface area problems, such as an elevator pit, will involve finding a centerline perimeter, multiplying it by the height, multiplying that by 2 to get the gross contact surface area, and then subtracting what's not there and adding back in any little bits and pieces. On page 315 of my edition, which is chapter 3, page 15, maybe a different page for you, we come upon some diagrams that can be instructive. Essentially, if we were considering that we were going to form this wall up, we could be asked a number of questions for the exam about this. For example, what's the contact surface area for the wall forms all along here? Now, if you remember, we had discussed in the very first module the idea of the centerline perimeter. If I want to find the real length of this wall, I can either chop it up into little pieces so I don't double count anything, or I could pretend I was standing on the top of it and measure exactly the length along the center of the top of this. That length along the center line represents the true length of this wall. If I were to open it up, forgetting any jogs, I would just open it up and extend it. That would be the true length. So if I knew the center line distance here, I could then just multiply it by the height of the wall and multiply it by 2, and that would give me the contact surface area for everything except for the little edges. You'll notice they refer to a moisture content of the lumber of 19%, and they indicate here that this 19% moisture is necessary, and the American Standard lumber at 19% moisture is what is called for when using forms. Table 4-2 on page 4-6 in my edition relates the various characteristics of lumber. What you have here is you have the various species and grades of lumber, and then you have the different characteristics by which you evaluate this lumber, such as its fiber bending strength, its compression perpendicular to the grain, its compression parallel to the grain. It then goes on to talk about its horizontal shear and its modulus of elasticity. What we're talking about here is the ability of the material to stretch and refabricate back into its original shape, and also its ability to withstand force coming at it from a direction with or against its grain. And they're listing the different capabilities of the lumber. Now, you probably will not have to go into this table But it's important to realize that later tables, when they're comparing one type of system to another, are basically using these factors to separate out the kinds of lumber from each other when they're evaluating their usefulness. Another issue involving formwork has to do with its ability to be reused. And notice that there's a bit of information here that says that a 7-day load duration is a calculation of the cumulative duration of the full maximum load. So any formwork likely to see more than 168 hours of maximum loading would not qualify for the stress increase based on the load duration. One of the more commonly used materials is plywood, which is really an engineered wood product. And what's important in dealing with plywood has to do with whether or not you have the grains and whether or not loads placed on the plywood is running parallel or perpendicular to the grains. This issue of parallel or perpendicular translates into a weak way and a strong way. And on page 411 in my book, they show you a picture of the weak way and the strong way. And if you have to go into the tables that we'll discuss later on, it's going to be necessary for you to visualize whether you're dealing with a span where the face grain is parallel to the span or where the face grain is perpendicular to the span. And notice they also mentioned here when dealing with grades and types that grade BB is commonly used for formwork. You'll notice also that from and around page 413, there's a number of other specific types of materials in addition to manufactured plywood that is also commonly used as form materials, and these are listed in subsequent pages. An important consideration, of course, is the fastening of the members of the formwork. And here we find on my book, page 424, that the sheathing, for nominal 1-inch sheathing or 5/8 inch and thicker plywood, 60 nails are recommended. And for panel form, common nails of the size are better because such forms must withstand considerable racking and abuse. So as a particular bit of information, we have that. But then we're going to have an analysis of the holding power of nails in a series of exhibits and tables that follow in the book. The first exhibit is a table right underneath the page I was referring to, which is table 4-6, nail sizes and measurements. Now, this book has changed editions. In prior editions, it was not necessary for you to get the diameter of a particular type of nail. For example, if you look here, you see a 10D, and you see a diameter in inches of 0.148. It used to be that there was a table that simply took the name of the nail, such as 10D, and then told you about its power, its holding power. But in this edition of the book, if we want to find out the holding power of a nail, we're going to have to use another table. But before we go to the other table, we're going to have to find out some sort of information about the particular nail we're using, in this case a 10D nail, and we may need to find out the head diameter or the nail diameter so that we can use another table to find out that it's carrying power. Here we see different types of nails that are typically used: box, common, and double head. A double head is used when you're only going to temporarily nail something and you want to pull it out later. You also have a conversation about toenailing and clinching and how that deals with the load factor. So for example, if we were looking at trying to figure out how much a toenail nail would have in terms of holding power, we would look for the withdrawal load from another table, and once we found that withdrawal load, we would multiply it by 0.67, and that would tell us the holding power of that nail. Another bit of information here has to do with plywood in particular, where we're told that the resistance to withdrawal of nails in plywood is 15 to 30% less than that of solid wood. So again, if we were going to calculate the holding power in a piece of plywood, we would go to a table and determine the general holding power of the nail, which is based on a solid wood, and then adjust it by 15 to 30%. Underneath this, there's the discussion of wood screws, and these, of course, are generally going to be stronger than nails in terms of holding value. Notice with wood screws, it does indicate that if the screws are wet, that is to say if the wood is wet and the screws are going into them, you may need to adjust the strength factor of the screw by up to 0.67 to account for the fact that it's wet. Table 4-7 is the one I was referring to before. Now, if you have a different edition book, this table will appear a little differently. However, what they're doing here is they're saying, given the nail diameter in inches, which we would have found by looking at another table, we can figure out the load holding power of the nail in a configuration like this. That is to say, how much is this nail holding? Well, let's say this nail was a 10D nail, and let's say that we were dealing with a spruce nail. We would look, or a southern pine, let's leave it at that because it's right at the top of the table. We would look under species of wood for southern pine. We would have looked for 10D nail in the other table to find out that it had a .148 size. We would then look down here and see that we've got a 46 number. Now that 46 is the allowable withdrawal load design value in pounds per inch of penetration. So we then would need to know the answer to the question, how far did this nail penetrate? If this nail penetrated 2 inches, then its holding power would be 46 times 2. If it penetrated, however, only a half an inch, it would be a half an inch times, a half times 46. Okay, so what we get from this table is the holding power of the nail per inch of penetration into the member. The next table on the next page relates to the holding power of nails, but now it's looking at the nail being inserted this way. And now this particular table doesn't make us translate anything. It tells us exactly to correlate the given name of the nail to the type of wood we're using. So if we had a 10D and we were using southern pine, we would see 121. And that again would be per inch of penetration. Okay, they call it 12 diameters penetration, but basically an inch of penetration, 121 pounds in the type of configuration that's shown at the top of the table. The book now continues to describe this with different types of fasteners, same type of concept. And it might be necessary for you to look at some of these tables to get an answer for the exam. The next topic in your book on page 4-32 deals with ties. And it indicates that twisted wire and band iron were once the chief tying materials, but they have low strength. And so now there are a wide variety of ready-made ties with safe load ratings ranging from 1,000 pounds to more than 50,000 pounds. Now remember, this safe load rating, that has that safety factor counted in. You don't want to use these things to the full point of their collapse. You want to give them some sort of a leeway. And they show you a picture of different holding devices and ties here. And then at the bottom of this exhibit of holding devices, they indicate that most of these ties are provided with manufacturer-suggested working loads ranging from 2,000 to 5,000 pounds. Taper ties have working loads from 4,500 to more than 50,000 pounds. And now they're going to differentiate these different types from one another. There is a continuous type talked about here, an internal disconnection here. And they refer back to the ACI 347 that has revised its recommendations about tie safety and uses a formula of 1.5 safety factor. And what that means essentially is that if I have a tie that's going to break at, say, 10,000 pounds, then I'm going to divide that by 1.5, and that's going to tell me what the safe working load of that tie would be. And they also recommend that a quick way to do it is just to use 75% of the given load value to take into account the 1.5 safety factor. On the next page, the book discusses or continues the discussion about the accessories and talks about anchors.